Okay, so actually in this chapter 25, okay, we'll introduce a circuit component called capacitor, and its characteristic, or one of its most important characteristic, is called capacitance. Okay, and then we will introduce how to calculate the capacitance of a capacitor given some specific structure like parallel plate capacitor, just as what we have learned in chapter 22. We try to have some parallel plate generate some uniform E field. Okay, and actually that was a capacitor. Okay, and yeah, so first one will be the parallel plate capacitor, and then we'll also calculate the capacitance of a cylindrical capacitor and also spherical capacitor. And then we'll talk about the parallel and series for capacitors. Okay, so just this is actually some of the circuit theory. Yeah, and then we'll talk about the energy stored in an E field or energy stored in a capacitor. Okay, and then finally we'll talk about the capacitor with dielectric. Okay, dielectric is it's a way to increase the capacitance. Of course, the capacitance is related to the geometric shape. Okay, if you need a larger capacitance, then probably you need to increase the cross-section area or make the distance between the parallel plate to be smaller. Yeah, so these two factors are related to the geometric shape. Other than that, you can also introduce something called the dielectric to really increase the capacitance if you want to. Okay, and then finally talk about the dielectric, how the dielectric influence the Gauss law. Just change the epsilon to epsilon. Okay. Okay, so so this is the definition of a capacitor. So a capacitor consists of two isolated conductors, the plates with charges plus Q and negative Q. Its capacitance C is defined as Q equals CV, or C equals Q over V, something like that. Yeah, when we talk about definition, usually more intuitive to put it on the left side and then equals to something else, and then it will be equal to the Q over V. Okay, V is the potential difference between the parallel plate, or in circuit theory we usually call it the voltage difference. Okay, so actually it's like this. So here we have the parallel plate, and if we try to apply some potential difference for this parallel plate, let's say if we just put a battery here, then there will be with a potential V, potential difference V, then there will be potential difference V between these two plates. Okay, suppose the wire is a perfect conductor, and then there will be V across these two parallel plates. So if we apply the potential difference there, then there will be some charges accumulate. Some charge accumulate on the plates. Okay, let's say if this side is positive for the top plate, and if the bottom plate is negative, then there will be, let's say, positive Q on the top plate, and then negative Q on the bottom plate. Okay, so bottom plate side of the top plate has a charge plus Q of the top plate. Bottom side of the top plate has the charge Q, and then the top side of the bottom plate has charge negative Q. Okay, so this positive Q and negative Q are in opposite polarity, so they will attract each other. And in such a way, there will be potential difference. and actually it will generate a uniform E field. Okay, it will generate E field mainly between the parallel plate, and of course there are some other E field lines outside. Okay. Okay, so here it says a parallel plate capacitor made up of two plates of area A separated by a distance d. The charges on the facing plate surfaces have the same magnitude q. Okay, same magnitude q but opposite sign. 因为它原来是不带电荷的，那你给了电压之后，它两边就会相等。两边会相等，它不能够一边多一边少，它两边都会带同样大小的电荷，但是正负相反介正端高电位的 potential 比较高的，它就会带正电荷 ；potential 比较低，那边就会带负电荷。然后 as the field line shows, the electric field due to the charge plate is uniform in the central region between the plate. OK， 所以它主要是说，如果你真的严格来看的话，它只在这个 parallel plate 的中间的部分是很均匀的。那它在靠近边缘的部分已经会变弱，已经会减弱，因为当时我们推导的时候，我们是假设一个是无穷大的一个 conducting plate 有带电荷的。那它就会产生一个 uniform 的 E field。那但是的话，现在我们不可能有一个无限大的一个conducting plate 嘛。那所以我们缩小这个范围的话，就是在比较里面的位置，它看起来就是外面还是很多，所以在里面的位置就会看到均匀。但是靠近边缘的地方，它就会看到这边是没有的所以那边就会比较弱，就是本来这边应该要有的话，它才会产生一个均匀的。那少了，那这边就会变弱，这那种感觉。Okay, so the field is not uniform at the edge of the plate. 接近边缘的已经减弱，而且在外面也会有。那我们就会叫这些叫做 fringing fringe effect 这个叫做 fringe effect， 就是这个就是边缘的一个效应的话，就是边缘的地方会比较弱在外面也没有。那实际如果我们要做一些简化的话，我们会假设说一个 parallel plate 的话，它在里面都是均匀的，在外面是没有的，在外面是没有电场。E 等于0在外面，简化的数学模型，然后 E 是均匀的uniform E inside between the parallel plate， 那这个是一个简化的，那就算起来就会简单很多。那这个的话就会比较正确，但是算起来就比较复杂，可能要一些什么 computer aided software 才能够算得很精确。那如果用手算的话，往往就是取一个简单的模型，就是外面是0，里面是均匀的。Okay, so here we talk about the charging capacitor. So when a circuit with a battery, an open switch, and an uncharged capacitor is complete by closing the switch, conducting electrons shift, leaving the capacitor plate with opposite charges. Okay. So here we have a battery. We have a battery, and then this positive side connect to a plate, and then the negative side connect to a switch, and then this switch connecting to the other side of the plate of the capacitor. Okay, so of course this is a better looking figure, but so simply, well, usually we will use some so-called circuit symbol， 就是一些电路的符号去代表这个图嘛，那画起来就会简单很多。So actually we'll use this parallel line, yeah, one with one will be longer to specify this is a battery, okay, and then this side is a positive, and then this side is a negative, okay, and then for the capacitor, we'll also use two parallel lines with the same length to represent this is a capacitor, and for the switch, it can be more diverse in different textbook. Yeah, for example, this one maybe it will draw it like this, or if I draw it, I will sometimes draw it like this. Okay, these two dots become hollow， 就是空心的，就是这样画。我自己画的话会这样，因为你要点成一个实心的点的话，就会很耗时间，那画两个圈就比较快。Okay, so actually it will be something like this: a battery. One side is connected to a capacitor, and then for the negative side of the battery connected to the switch, and then switch also connected to the other side of the capacitor. Okay, it will be something like this. So a battery B, a switch S, and a C are interconnect Y form a circuit. The same circuit shown in the schematic diagram, in which a symbol for a battery, a switch, a capacitor represent those devices. Okay, yeah, so nothing special here. Okay, so let's go to the next page. So here we try to calculate the E field generated by the parallel plate capacitor. And here it says to relay the E field between the plates of a capacitor to the charge Q on either plate, we shall use Gauss law. Okay, 所以这里我们就需要用到高斯定律。Okay, so here we use Gauss law to relay Q and E. Then we integrate the E to get the potential difference. Okay, so the idea is like this. Here we have the capacitor shown in the blue color, and then this one has the highest potential, this one has a lower potential, and we define the Gaussian surface like this. Okay, this is a rectangle. This side is inside the positive plate or the positive terminal of the capacitor, and then the other side is right between, and then these two sides are somehow here. Okay, so let's see, and then here we try to define this point to be the initial point, this point to be the final point. Okay, the initial point is at the negative terminal, is in the negative terminal, and the final point is in the final terminal. Because it's a conductor, so the whole conductor should have the same potential. So which means that we try to have the potential difference. The potential difference here will be like a V. V will be the potential difference between the positive plate and the negative plate. Okay, so in such a way, we define a path from the initial point to the final point. So we try to use this definition. Vf minus Vi equals negative of integration of E dot ds from I to F, to get the relationship between the E field and the potential difference between the plates. And also we will apply the Gauss law for this Gaussian surface like this. Okay, so at the beginning the Gauss law is nothing but this. And actually, just now we mentioned that the positive charge will be at the bottom side, will be at the bottom surface of the top plate. Okay, so the positive Q will be in this Gaussian surface, and actually the negative charge are outside the Gaussian surface. So Q enclosed is actually this Q enclosed is actually this plus Q, not all the charge. If the total charge will be 0 plus Q minus Q, then it will be 0. But yeah, as much as we define the Gaussian surface like this, the Q enclosed is only plus Q. And usually, for simplicity, we will just express the potential difference as V. Okay, so V will be nothing but Vf minus Vi. And originally, the definition is like negative integration E dot ds from I to F. And actually, yeah, with some computation or with some simplification, we usually will try to consider this path is line parallel to the E field, so E dot ds is nothing but EDS, and yeah, so by combining some of the negative sign, it turns out to be something like we integrate EDS from negative to positive, okay, which is something like this. Yeah, because originally it has a negative sign, and the ds will be something like this. So, and then you consider this is a positive plate, this is a negative plate, so the E field pointing downward, E dot ds will be negative. So this negative sign will cancel with this negative sign. So it turns out to be a positive value, something like this. And actually it looks cleaner. Okay, so V is actually the integration of E dot ds from negative to positive. So yeah, makes much sense. Okay, so here, yeah, we'll try to simplify this Gauss law. Okay, so on the right side is nothing but Q, but on the left side, originally, it will be integration of E dot dA, and here we will, yeah, here it actually mentioned the approximation I just mentioned about. So it says we assume that plates of our parallel plate capacitor are so large, so close together that we can neglect the fringing, 就是忽略那些边际的效应. Okay, so of the E field at the edges of the plates. Okay, so we will just consider taking E to be constant throughout the region between the plate, and it will be 0 outside the plate. Okay, just as what I mentioned. Okay, so in such a way, when we consider the flux for net flux for this Gaussian surface, for the top surface, it is actually inside the conductor, so E will be 0, so it won't contribute to this surface integral. And for this side 0, for this side 0, so these three sides won't contribute to this surface integral. So only this surface will contribute. So as much as this is a surface integral, this is a Gaussian surface, dA, okay, dA is actually pointing downward, okay, for this surface, and the E field also pointing downward. So it is something like E times dA, and then E will be constant. E will be constant throughout the parallel plate. Okay, so in such a way E is constant, so it is nothing but E times A for this parallel plate capacitor. So finally, it turns out to be like this. And then, yeah, in the previous page, we also have this V equals integration of EDS, and E is actually a constant, so E can be put outside. So this is a line integral, but integrating a constant. So it's just the length of the line, or it is just the length of this path. Okay, so we just note the distance between the parallel plate to be small d. Okay, so this one is nothing but d. So this is v equals ed. V equals ed. Okay, and then so here we have e equals v over d, and then we can put this one here. So here we have epsilon naught v over d times a equals q equals cv, which is the definition of the capacitor. Okay, so here we have q equals cv. Okay, so in such a way we can cancel v and v on both sides. Finally, we get c equals epsilon naught a over d. Epsilon naught a over d. So actually, this is the expression, the closed form expression for the parallel plate capacitor. Epsilon naught is the constant, the permittivity constant. Okay, and a is actually the cross-section area. Cross-section area means the cross-section area, the plate. Okay, the cross-section area of the conducting plate. 就是那个截面面积, and then the d is the distance between the parallel plate. Okay, so which means that if we would like to have a larger capacitance, we would like to increase this area, or we would like to make the distance between the plates smaller. Okay, to make a larger capacitor. So actually, the capacitance is actually related to the geometric shape， 跟它的几何形状有关，就是截面面积越大，它的那个电容值才会越大，或者是那个平行板的距离越短，那个电容值也会越大。Okay, so let's stop here.